Welcome back to Chemistry Matters. In this unit, we're talking about equilibrium in our everyday lives. Our first two segments on equilibrium introduce the concept of chemical equilibrium, how it's related to the rates of reaction, and how it's measured. In this video, we'll talk about how equilibrium is relevant to us. If you did the assignment at the end of the last video, by now you should have thought of some systems in your daily routine that are in equilibrium. Let's go back to our classroom and see what systems our students have come up with.
Equilibrium plays a very important role in our lives. In a moment, I'll give you a few examples, but first of all, I'd like to hear what you guys have. Who has a system in mind in which they think it must exist in equilibrium?
What about a swimming pool? I work at one during the summer, and I always have to check to make sure that the pH is between 7 and 7.6.
That's right. So what is it about a swimming pool that is in equilibrium? And what do you think would happen if the swimming pool was not in equilibrium?
It's the pH that's in equilibrium, and if the pH gets too high or too low, swimmers' eyes might sting, or bacteria might grow.
Good example, and you're right. The reaction that's taking place in a swimming pool is actually an acid-base reaction. And if you go back to what we learned in Unit 1, the pH that's most favorable for a swimming pool is very close to neutral. So how about you two?
Well, I was thinking that the air we breathe has to be in equilibrium. We have oxygen that we need to breathe, and plants need carbon dioxide, so it has to stay balanced.
That's a very important example. And I like how you use one of our criterion to describe an equilibrium system: stable, balanced, or unchanging. As a matter of fact, the Earth's atmosphere also exists in dynamic equilibrium. The gases that make up our atmosphere enter and leave by way of chemical reactions, dissolution in water, and absorption into the Earth's crust.
As our teacher just mentioned, the Earth's atmosphere is a very important example of everyday equilibrium. In fact, our very lives depend on equilibrium in lots of ways. For example, our blood has to stay close to a pH of 7.4, slightly basic but close to neutral. Our bodies maintain carbon dioxide, carbonic acid, and hydrogen carbonate in just the right concentrations to keep our blood at the right pH. If our blood pH is greater than 8 or less than 6.7, we die. Our cells also maintain an equilibrium concentration of electrolytes. Electrolytes are charged particles, like sodium or calcium ions. We have to have a certain concentration of these electrolytes for our hearts and brains to work. Electrolytes carry the electrical signals that tell our brain and heart when and how hard to work. If we don't have the right concentration of electrolytes, we might experience mental confusion and an irregular heartbeat. If you've ever gotten dehydrated through sports or other activities, you've had an imbalance in your electrolytes. So if our bodies have to stay in equilibrium in order for us to stay alive, you might be wondering how they get back into equilibrium after being knocked out of equilibrium by something like dehydration. And that leads us to our next topic: reestablishing equilibrium after a system has been stressed. A chemical equilibrium can be stressed by changing a number of factors, but equilibrium is reestablished as the reaction shifts toward products or reactants. The principle of chemical equilibrium, discovered in 1884 by the French chemist Henri Le Chatelier, states that when equilibrium is disturbed or stressed, the system adjusts to reestablish equilibrium by minimizing or countering the stress. Imagine someone trying to pull you out of bed when you're sound asleep. You'd probably respond by pulling in the opposite direction so you could stay in your nice, comfy bed. Le Chatelier's principle says that equilibrium can be stressed or taken out of equilibrium in one of three ways: by changing the concentration of the reactants or products, by changing the pressure or volume of a system that contains gases, or by changing the temperature. And of those three, temperature is the only thing that can cause the equilibrium constant, or the ratio of products to reactants, to change. Now let's get back to our classroom to learn more.
Let's look back at the Haber process as an example. Imagine we're all chemists working in a manufacturing plant, and we are responsible for producing the maximum amount of ammonia. So our reaction has reached equilibrium, and the amount of ammonia made is less than what we want. So what do you think we can do to disturb the equilibrium so that we can produce more ammonia?
We could add more reactants, right?
Yes, if we were to add more nitrogen or hydrogen gas to the reaction, the ratio of the products and the reactants would change, and there would be excess reactant. And Le Chatelier's principle tells us that the equilibrium would be reestablished by consuming the extra reactant, thereby making more products. So we say the reaction shifts to the right to reestablish the equilibrium. Can anyone think of another way that we could increase the amount of ammonia formed?
What if we raise the temperature?
Okay, that's a good idea because temperature definitely affects equilibrium, but an increase in temperature will speed up both the forward and the reverse reaction. So depending on whether or not the reaction is endothermic or exothermic, the reaction might produce more reactants or it might make more products. And we'll talk more about temperature changes here in a little bit. There's one other way that we can stress the equilibrium. Carter, can you remember?
Well, the reactants and products are all gases, so a change in pressure should disturb the equilibrium.
That's exactly right. And according to Le Chatelier's principle, how will the reaction respond to an increase in pressure? For example, if we reduce the volume of this system.
Le Chatelier's principle says that the reaction will try and minimize the disturbance. So the reaction should shift to reduce the pressure. But I'm not sure how a reaction can reduce pressure.
Well, we learned when we investigated gas laws that pressure is caused by collisions of gas particles with the container it fills. So to reduce pressure, we have to reduce the number of collisions. I think we have to have fewer gas molecules, but I'm not sure how to do that.
That's excellent reasoning, and you're definitely on the right track. So let's take a look back at the Haber process to see how we can reduce the number of gas molecules. And what I'd like you to do is take a look at the coefficients in the balanced equation, and according to Le Chatelier's principle, which direction would this need to shift in order for us to have fewer number of gas particles?
The right side, that's the product side, right?
Yes, absolutely. So how can you explain what you've just figured out?
Well, there are only 2 gas molecules on the product side and 4 on the reactant. So fewer gas molecules means less pressure. So shift towards the product side will reduce pressure.
You've done a great job of explaining a very difficult concept. And what we've just done is come up with another way to increase the amount of ammonia that would be produced via the Haber process. An increase in pressure or a decrease in volume in the system will result in production of more ammonia. And there's one more way that we could increase the amount of ammonia produced, and it involves changing concentrations again. And we've already talked about how adding a reactant would cause a shift towards the right, but let's look back at the Haber process one more time, and let's see if you can think of one more way that we could change the concentrations of the reactants or the products to make this equilibrium system shift to the right. What do you think, Emma?
We've already changed concentrations of the reactants, so I guess it must involve the product. We can't add more ammonia because that would make the reaction shift back toward the reactant, wouldn't it? I'm not sure what else we could do to make more product.
You're right. If we added more ammonia, it would cause the reaction to shift back towards the left in order to consume that extra ammonia that we just added. Let me give you a hint. Let's say that we had coffee and we needed to provide coffee for 100 people, and your coffee pot only holds 10 cups. What would you do?
Go to a coffee shop and get more?
All right, let me rephrase the question. How could you use your 10-cup coffee maker to make enough coffee for 100 people?
Just empty the 10 cups into another container after each batch so you can make more.
You're right.
So could we empty the ammonia out of the reaction when it's made in the Haber process?
We sure can, and as a matter of fact, that's exactly what manufacturers of ammonia do. They remove the ammonia as it's being produced, and that disturbs the equilibrium position because it makes the equilibrium position shift to the right, thereby making more ammonia. And I think this will be easier to understand Le Chatelier's principle if we watch it in action. Le Chatelier's principle is in play all around us, but it's easiest to observe this when there's a color change. So let's see what happens to this tea when it encounters something like our stomach acid. So tea gets its dark color from a complex substance called thiorubigen. Now, thiorubigen has no color when it's in its solid neutral state. However, when it's dissolved in water, the substance acts as a weak acid. And when it does this, it partially ionizes to make the thiorubigen anion, as well as a hydrogen ion. And so the neutral and ionized substances are in equilibrium, and therefore they are subject to Le Chatelier's principle. And I know these molecules look complicated, so for simplicity, let's just call thiorubigen T. and let's call its anion the T anion. So you see in front of you here 4 flasks, and each one of them contains the same concentration of black tea. And we'll leave this flask here as our control so that we can go back and reference and see what the initial color was. So using Le Chatelier's principle as a guide, who can suggest a way that we could change the color of the tea solution?
Couldn't we just add more tea?
Yes, we could. Can you explain in terms of Le Chatelier's principle why dissolving more tea into the solution would cause the color of the solution to darken?
Well, dissolved tea is the reactant, and if we add more reactants, the reaction should shift toward the product.
Good. And the more products there are, or in other words, the tea anions, the more color we should have. So let's think of another way that we could change the color of the tea. Can anybody think of a way that we can make the solution lighter?
You would have to shift the reaction towards the reactant to make it lighter, but I'm not sure how to do that.
Okay, you're right. Does anyone know a way that we can cause the equilibrium and the reaction to shift towards the reactants?
You have to add more products. Could we just add more hydrogen ion?
Sure we can. Hydrogen ions are present in all aqueous acidic solutions. And I'm going to add a squirt of lemon juice, which contains plenty of hydrogen ions due to the citric acid that is contained in lemon.
It got lighter, just like we thought.
Can anybody explain why the color of the tea solution became lighter when we added the lemon juice?
I think I can. Since lemon juice is acidic, that means it has hydrogen ions. So if we add more hydrogen ions to the tea, Le Chatelier's principle says that the reaction will shift towards the reactant to try to use up the extra hydrogen ions.
I get it, and when the reaction shifts towards reactants, the dark color goes away.
Excellent. So now let's stress the reaction in one more way to see how it responds. And what I'm going to do next is add some baking soda to the solution. Now, baking soda contains sodium bicarbonate, which is basic. So who would like to predict what will happen when I add a base to the solution of tea?
Well, bases react with acids, but I'm not sure what that'll do to the equilibrium.
Well, you're right. The baking soda is a base, and it will react with the acid. So let's watch what happens to the color of the solution as the baking soda is added.
Okay, so the base reacted with the hydrogen ion on the product side. That made the product go away, so the equilibrium shifted towards the product side to replace the hydrogen ion that has been lost.
You got it.
I don't understand this one. It seems really complicated.
Yeah, this one is pretty complicated. So let's look at what's happening using our balance again. So when we add a substance that reacts with the product, the concentration of the product begins to decrease, and that causes an imbalance in equilibrium. And so the reaction is going to respond to this imbalance by shifting towards the right, and that's going to make more products. And so I think we should summarize what we've learned so far about Le Chatelier's principle, and then I'll give you guys a chance to work hands-on with the system in equilibrium. So let's summarize the ways that we've learned how to disturb an equilibrium and how Le Chatelier's principle will allow us to predict how the system will respond to that disturbance. Who can tell me one thing that you've learned about Le Chatelier's principle and disturbing an equilibrium system?
If you add more reactants, the reaction will shift towards the right, towards the products.
And if you add more products, the reaction will shift towards the left, towards the reactants.
Good. We've talked about increasing reactants or products. What about if we decrease them?
If you take away products, the reaction will shift right to make more products.
So I guess you could take away the reactant, and the reaction would shift to the left to make more.
Great job. Now, let's see if we can remember how changes in temperature and pressure can disturb an equilibrium. Let's assume that the ionization of thiorubigen is endothermic, which means that the process absorbs heat from the surroundings in order to ionize. So heat can be thought of in this situation as a reactant. And so if you look at the reaction containing heat as a reactant, what effect do you think heating this reaction would have according to Le Chatelier's principle?
Well, adding heat would be like adding more reactants. So the equilibrium would shift towards the product and use up that excess heat.
And that's exactly what would happen, Carter. Can you explain what happens according to Le Chatelier's principle if we were to cool the reaction?
I'm not sure, except cooling is the opposite of heating, so maybe the reaction would do the opposite.
Yeah, you're on the right track. So let me give you a hint. We cool something by removing heat. So why don't we put our control flask into an ice bath, and by doing this, we are cooling it, or in other words, removing heat. Now, this one takes a little while for it to be something that we could observe, but what do you think would happen after about 10 or 15 minutes?
Oh, I get it. Since the reaction is endothermic, when we cool it, we're removing heat from the reactant side.
So according to Le Chatelier's principle, the reaction will shift left towards the reactant.
Exactly. It will take some time, but after about 15 minutes or so, what do you guys expect that we would see from the flask?
It'll get lighter.
Exactly, because like we were saying earlier, by adding it to the ice bath, we're effectively removing heat from the system, and that's going to pull the equilibrium system to the left. And as we can see here, that means it will get colorless.
If you've followed along with our students' review, by now you should be pretty familiar with our friend Henri Le Chatelier. So let's set up an experiment using everything you've learned so far about equilibrium. In our next segment, we'll be planning and carrying out an investigation of the equilibrium of smog. And you'll get a chance to use the knowledge you've gained from the prior videos in this unit to better understand a real-life phenomenon, the formation of smog pollution. I'm holding a sealed glass tube with a mixture of two gases, nitrogen dioxide and dinitrogen tetroxide. These gases are in equilibrium with each other and play an important role in the formation of air pollution. Let's take a look at the chemical equation for this equilibrium. Under certain conditions in the atmosphere, two molecules of nitrogen dioxide can combine to form dinitrogen tetroxide. Interestingly enough, one of these two gases is colorless and the other is brown. The brown gas is the main component of smog. You may have noticed that certain areas of the country, and of the world in fact, have worse smog than others. And you may have noticed that certain times of the year and particular weather conditions produce more smog than others. Smog is worse in areas where lots of fuel is burned and has traditionally come principally from motor vehicle exhaust and utilities. You're going to investigate this equilibrium and conduct research about the formation of smog. Your first job is to design and carry out an experiment that will allow you to identify which gas is responsible for smog. Secondly, through research and data analysis, you'll explain the relationship between these gases and the smog we see in many cities. Before you begin planning your investigation, let's discuss the variables we can test. The ideal gas law tells us that the properties of a gas can be changed by modifying one of four variables: pressure, volume, number of moles, and temperature. Our two gases are in a sealed tube, so as you plan, discuss with your group which of these conditions you can control. Notice that the combination of nitrogen dioxide to form dinitrogen tetroxide is an exothermic reaction. It releases heat. Of course, the reverse reaction, the decomposition of dinitrogen tetroxide to reform nitrogen dioxide, is endothermic, meaning it must absorb heat to occur. In order to plan this investigation, you'll need to understand the effect of temperature on equilibrium. A simple way to understand this is to think of heat as acting like a product in an exothermic reaction and like a reactant in an endothermic reaction. Your goal in this investigation is to design and carry out an experiment that will allow you to identify which gas is responsible for brown smog. This should be the identity of the gas, not its color. And remember, as a scientist, you must also defend your conclusions based on data. Use literature research and data analysis to explain the relevance of this equilibrium to the smog we see in many cities under a variety of conditions. Before we begin the investigation, it's important to develop a detailed materials list and procedure. For example, what will you test? How will you test it? How many times? At the end of your planning, you should have detailed a procedure that any scientist could follow to conduct an investigation. A materials list should be pretty straightforward. Each group will be using these sealed tubes. But what else will you need to complete your investigation? If you want to review how to plan an experimental procedure, you may want to rewatch our Unit 1 Introduction to Chemistry video. Keep the primary question of the investigation in mind while you're writing your procedure, and make sure that the procedure will generate data that answers the primary question. The data will be your evidence to support your claims. For now, we'll stop here to give you a chance to go over your materials list and your procedure for this investigation with your teacher. After that, you can meet me at the top of the next video, where we'll begin our investigation of the equilibrium of smog.